Aloha, Richard Halverson here, and we are going to finish up the remainder of Chapter 6 today. There's some important stuff that we still need to cover after the after you've started your encryption assignment. And so let's get started. I'm going to share my screen. Hello again. Let's see. So we are in Chapter 6, and these were the slides. If you recall, we've covered the Boolean and comparison instructions, conditional jumps, conditional loop instructions. You recall to do the assignment we used. No, we did not. I think this might be where we start in this chapter list. So let's for the remainder of this. So let's go through to let's find. It's about. Covered these applications, the test instruction, compare, Boolean instructions, what's next, conditional jumps. We did conditional jumps, JZ. And we ended with the encryption string. Here's where we are. Okay, bit test instruction. Okay, so with this instruction, you can just test a specific bit, and you identify this. So this might be useful if you're using the bits of words as set for set membership, and so it's just the BT9, for example. If it's syntax. Jump to label bit 9 is set. Okay, so that's how that works. If bit 9 is set. All right. And it must set the carry. Copies the bit n into the carry flag. Right. Okay, so copies bit 9 of the AX register into the carry flag, and then you use a jump at the carry. All right. Next, the conditional loop instructions, and these are just like the loop instruction, which just counts down the CX register, ECX register, as you know, but also does a test if 0 or test if equal. So we start there's two of them, loop if 0, loop if not 0, and they can also be used as loop if equal and loop if not equal. So the syntax is you have loop if equal goes to a destination, and the way it works is it decrements ECX just like always, just like the plain old loop. But then what it does is for this one, if ECX is greater than 0 and the 0 flag is set to 1, then it jumps to the destination. So in other words, if you normally it's just if ECX is greater than 0, but also the 0 flag has to be equal 1, which indicates something was equal. Okay, so this is going to count either to it's either going to count down ECX down to 0 if the 0 flag never gets set to 1. No, wait, if the 0 flag is always equal to 1. Okay, well, there's an I get these mixed up of when you should use equal and 0 because of jumping and not jumping, and you know how you sort of jump around what you want to do and so on. So let's cover these, and then at the end of this section, there's a nice example which clears it up pretty good. So we have so if ECX is greater than 0 and the 0 flag is 1, in other words, it was equal, it's kind of like loop while it's equal, and then if it's not equal, or ECX goes to 0, then it falls through. See, so So this is useful when scanning for scanning where you're trying to find the first element that does not match a value, because if it matches, it's going to keep on looping. So anyway, that's what's next. This is the not zero, and it's kind of the opposite of before. We're still going to loop. The jumping to destination means we're still going to loop. We're still in the loop. We're still in the loop as long as we haven't counted down to zero yet. And we've been getting not non-matches. So it loops as long as you're getting non-matches, and it stops looping when either you get a match, in other words, the zero flag is equal to 1, or if the ECX counts down to 0. Useful when scanning for an array element, for the first element that matches. So here's an example. We're going to try to find find the first positive value in the array. So we're going to go through this array, and we're going to find the location of the first positive value. And so this is the location. This finds the address of it. So this is the first positive value. So this is what we're after. So we look at the ECI, or no, we load the starting of the array into ECI. This is the counter, so we're going to count all the way to the end, and we're either going to get all the way to the end, or we're going to stop when we find a positive number. So here, testing. We do it by looking at the sign bit. If the sign bit, the very highest order bit, if that's a 1, then we have a negative number. Otherwise, if it's not 1, then we have found a positive number. So this tests the word pointed to by ESI with 8,000 hex. Remember, test is like anding. So it's anding the highest order bit with 8,000. So when the anding is done, if it's positive, it'll be 0. If it's not positive, in other words, if the upper order, highest order bit was a 1, and it's ANDed with this hex value with the highest order bit 1, then it's going to be the same. It's going to be 8,000, and we will know that we're still in negative number territory. So we do this test, and that sets the flags. Doesn't change this value. It doesn't change the value. It just sets the flags, and then we're going to push all the flags, and we're going to increment the ESI pointer. We're going to pop it back out again because we have to increment the ESI pointer, which is separate, from this. So we test this, and then we increment the ESI pointer to here, and then we actually check and do the loop thing. See, we do the test, which sets the flags. We push the flags. We increment the ESI pointer. We pop the flags, and then we do the loop thing based on what the flags were. So we do the loop thing based on what the outcome of this testing of the sign bit. And we're doing NZ, so we're going to loop back up here as long as ECX is greater than 0, and as long as we did not, it's a not 0, or a if the result of the last operation was 0, then this test resulted in 0, in which case we looked at a positive number. But since the result of this test is not 0, it's 8,000. This loop is going to be taken. So this loop keeps on being taken until it finds this number. So it'll do the test. It's doing 10 now. Okay, it's doing 10. It tests, and so with 10, the highest order bit is 0. So this is 10. This is 10 here, and we're ANDing it with 8,000. Highest order bit is a 1. Okay. Then we push the flags. Then we increment ESI so it points to 30. We do the increment first, and then we do this loop jump. Okay. We pop the flags back out. Then we do this loop jump, and ECX is not equal is not up to the top yet. It's only 1, 2, 3, 4, 5. It's not it can go all the way up to 8. So that passes. However, when you did this test, the result is going to end up 0 because 8 highest order bit ANDed with 0. A 1 ANDed with a 0 is going to be 0. So the result of the test is going to be 0. So this is going to fall through. It's going to fall down because this only loops if it's not 0. If it's 0, it doesn't loop. It falls down. So it's going to jump. If it's not 0, okay. So it's 0. It's 0. So it falls through, and then what it does is it checks to see. See, there's 2 ways it could have fallen through. It could have fallen through because ECX reached 0, or it could have fallen through because it came to a positive number. And so we have to test which it is. And so if it fell through because ECX was because ECX went to 0, then let's see, this is going to be well, if it found it, then if we were looking for 4, then we would have found it, and it'll equal 0. So if it's equal to 0 and it gets to here, that means that we found a positive number. So that means it's not going to jump to quit. It's not going to jump out. It's going to do this first. And what does that do? You remember it was pointing to 30, and we got to bring it back 1 because we already did this increment here. So we got to reverse that. So we subtract. Now we subtract the size of the array or the size of an element instead of adding here. So we basically reverse this last operation, and so then at the end, ESI is pointing to that. So that's an example of the LOOPNZ. All right, so you can fiddle around with this. This is looking for the first non-zero value in the array, and this is the solution. Okay, what's next? Conditional structures. Okay, so here we try to mimic higher level language constructs or structures. So we like to do block structured if statements. We like to do compound expressions with an and, compound expressions with an or. We like to do while loops, and we can even do these table driven selections, which are kind of like case statements, or what are they called? Switch statements, or whatever language you're in the if structure. The if else if kind of structure. Okay, so for block structured if statements, they look like this. Yeah, this is what a C whatever version looks like, and so that would translate in assembly language as something like this. Okay, so first we have to do this comparison. So we want to put op1 into the EAX register. Then we want to compare to see if it's equal to the op2. And if it's not equal, we want to go here and set x equal to 2. If it is equal, it falls through and it sets x equal to 1, and then it jumps out. So if they're equal, it does this and then jumps to L2. Or if it's not equal, it jumps to L1, which sets it equal to 2, and then it falls down here. So if it's equal, it sets it equal to 1. If it's not equal, it sets it equal to 2. See, so that's how you would implement something like this in assembly language. And since we've all learned higher level languages before we've learned assembly languages, we probably would tend to think this way. And so and that's a good thing, okay? So you want to think in these block structured constructs when you're writing your algorithm, and then you want to just kind of do a mechanical process thing where you just translate it over to this. And in fact, this is exactly what a compiler does. A compiler reads these things and produces this code. So here's some examples. You can do some other kind of stuff. This is for this kind of structure. This is the assembly language. For this kind of structure, assembly language. You can do this kind of stuff, and where you want to have compound expressions like this. And so you can, looks like this. There's more than one kind of implementation. And so here we basically compute this, and if this ends up being true, we compare A1 with B1. If A1 is greater than B1, then we jump to L1. Otherwise, we're done. See, so if this is true, then we have to jump and test this. If this is not true, then we can just jump out to afterwards, because we know the whole thing's not going to be true. So that's how it would be implemented, you see. And so the compiler is usually smart enough to recognize that. And that's why in a lot of higher level languages, when you do have compound expressions like this, this side, it would not be computed if this is evaluated to false. And here's another example here. But the following implementation uses 29% less code. By reversing the relational operator, we allow a program to fall through to the second expression. Okay, so I guess you can kind of see how this is only, 1 to whatever, and this means we jump around. So that's, optimization type stuff. Okay, your turn. Look through that. The answers are here, so it's helpful if you don't understand something and you can find an example. Or if you actually want to implement one of these structures, you can come to these slides and just basically copy the code. Okay, so, we like to do while loops. This is an example how you would implement a while loop. We do the comparison. And if it is, we're comparing if EAX is less than EBX. So we do a comparison, EAX, and we jump if above or equal. So in other words, we jump if this fails. If this is false, then we jump out, and that's what this is. This is the jumping out. Otherwise, we do what's inside the loop and jump back up and do the comparison again. All right, you can look at that, see how the implementation of that works. And we have this table driven. We can do these lookup value type things, and suited to large number of comparisons. It's like a case or switch or whatever language you're in. What it's called. Let's see. You actually okay. So for something that looks like this, process A, process B, process C. If this is the lookup value, so it looks like this, where you have the lookup value, and then you have this address of where you jump to if that's the case. And then you have this other lookup value, and you have this. So if it's A, it's going to jump to this one. If it's C, it's going to jump to this value 040. And so that's how it's going to work. So if it's, yeah, this is, all right. So this is how we'd implement it. We compare with, so EBX is going to be pointing to the value in the case table. So it's going to be, starts out by pointing to the character to compare. And if it's not equal, it jumps out, okay, and goes and compares the next one. Okay, jump if not equal to L2, which jumps it, so that it goes like down here and then out and back up here again. If it's equal, it's going to fall through and do this stuff. It's going to fall through and do this stuff and then jump out to the end. And what this is this is a call to this location. So this location is the address of the procedure to execute. And so this is a pointer to EBX plus 1. Well, EBX plus 1 is going to be this address, but this is not data. This is actually a program address. Okay, so it's kind of like you got. Okay, so you wouldn't see this in assembly in a higher level language, probably, but so so you're calling to a physical address that's been stuck in that table there. So that's how that works. All right, finite state machines. Finite state machines are very interesting, and if you're ever doing workflow or programming that, or this is more of an electrical engineering kind of topic when you're designing how processors sequential logic is executes and so on. So it's kind of interesting, but you can implement these things very easily in assembly language, and so you might want to simulate that. And so this is or like for example, compilers do this would do this at a lower level, although this code would probably be written in a higher level language. But this is a finite state machine which determines if something is a digit. Maybe this one's better. So you start out by, you can have a plus. You can have is this a variable? This recognizes X followed by the letters A through Y. X, and then as long as it's A through Y, it keeps on in this loop, but once it hits a Z, it quits, goes to C. So anyway, this is how you'd implement that. The last thing is flowchart. You can implement these kinds of things pretty straightforward. This is how you might describe some code that should be written in assembly language. All right, so the last thing in this chapter are these conditional control flow directives. And this is where these are runtime expressions, can use relational and logical operators, and it generates assembly language code. Okay, and there's a repeat and there's a while. There's these if, else, if, and so you just write this, or I guess you can write this. You write that, and the assembler produces the assembly language to convert that into something that works. Okay, so you really can think in these higher level language structures and write them that way. And the assembler will take care of assembly. So this is getting close. It's on its way towards the assembler actually implementing a higher level language. Okay, but there's no optimization or anything. It's just straight translation. Whereas a compiler, goes in and looks, and it'll make adjustments. Like if you are assigning something inside a loop and it never changes, it'll take that assignment outside the loop and that kind of stuff. So and these are the kinds of expressions that it implements. These just as all that you'd expect. These are carryover flow parity tests. So something like this, where you would have if EAX is greater than val1, then do that, and if it just automatically generates this code. For signed and unsigned comparisons, There's a repeat. Repeat is like this is, it was called repeat, and this is exactly like Pascal. Repeat until something happens, and it's like a it's like a do while. It's like a do while loop in C sharp. Is do while, is that in C sharp? Anyway, it's where the test the test is at the end. So the loop is going to be executed at least once, or it's going to take at least one pass through the code, and then at the end it's going to decide whether to go back up and do it again, and the decision is at the end. The difference between repeat until and a do while is that the condition is expressed, the opposite, where do while this is true, would loop, whereas until means do this while this is not true, because do this until this is true. See, so anyway, so there's a repeat directive, and there's a while directive, which is just like the regular while loop that you're familiar with. And so, to summarize here, we've learned about these bitwise instructions, how to manipulate individual bits and operands, why we would want to do that. We learned about the compare instruction and the test instruction, which does these operations but doesn't actually do them. It just sets the condition flags. There's a bunch of different conditional jumps and loops that are convenient, and we've got a lot of flexibility there. And flowcharts as a logic diagramming tool, which for writing defining what your assembly language is going to do, and finite-state machines, and so on, and then the directives. So you can figure out what that is. Those are ASCII codes. And so that finishes up chapter 6, and so next week we'll move on to chapter 7. Thanks for watching.